talk now is from Victor van de Veen, right? And he's coming from Amsterdam, and he will tell us a few things about Drammer Flip Feng Shui Goes Mobile. Victor, the floor is yours.
Thank you. So I'm Victor van der Veen. I'm from Vrije Universiteit Amsterdam. I'm very happy to be here again at the Android Security Symposium and talk today about Drammer Flip Feng Shui Goes Mobile. So that means I'm going to talk about two things, Drammer and Flip Feng Shui. A little bit about our group. So I'm Vrije Universiteit. I'm a PhD candidate and I'm in the System and Network Security group. But recently we've rebranded ourselves into FUSEC. We have a website, FUSEC, and basically everything in our group revolves around this guy. It's Herbert Bas, he's our professor, and then all the other people are very smart people standing around him. We do many cool stuff, or at least we think we do cool stuff. Today I'm talking about hardware vulnerabilities, but we also do research on the other topics. I was actually last week at NDSS and I was able to present work of a colleague of mine, Sanjay, on software testing. So we have a new fuzzer that I presented there. I also know everything about fuzzers now. Before Drammer, I did research on binary armoring. So I'm trying to protect binaries against code reuse attacks or ROP attacks. We also do malware analysis. So we were involved in bringing down the Game Over Zeus botnet a couple years ago. On the topic of hardware vulnerabilities, we also recently had a paper at NDSS on side-chaining the MMU to break ASLR from JavaScript. So we do a lot of cool stuff, and today I'm going to talk about two things. If there's something after today that you should remember, so you take away a message, is that we can now do rowhammer on ARM. We can use rowhammer to do reliable exploitation, and it also works on a Google Pixel. So by the way, who here is familiar with rowhammer? Okay, quite some people. For those who are not familiar, I'm going to explain this in a minute. Flip Feng Shui is basically a set of 3 papers in 2016, all published at top-tier scientific venues. And it is actually the art of turning a bit flip with rowhammer into reliable exploitation of the cloud, of the browser, and the mobile. So these are 3 papers that we published. Today I'm going to talk about the cloud, how we use rowhammer to break the cloud, and how to use rowhammer to break the mobile. The first paper we did was breaking the browser. So we have an attack against Microsoft Edge. I'm not going to talk about that today because it's too difficult, or at least I don't know much about it. But I'm going to discuss the other papers. But this is some promotional a bit of the talk. First time a couple weeks ago, I gave this presentation to a Dutch company, and I wanted to highlight that these are Dutch papers done by Dutch researchers and presented at top venues in computer security. And actually, also in 2016, one of the ranking lists put us on first place, better than MIT, because of all our cool publications. We also had worldwide impact, besides from publishing at scientific venues. We had articles in Ars Technica and Wired about a lot of the things we do. Also here in Austria, is it there? Yeah, there's Standard, had an article. And this comment was, I think, the most funny one from all the work we did. It was on Slashdot, on Drammer. So if you then look at the comments that people post below articles on Slashdot, there was this one guy saying, yeah, these are a bunch of pasty-faced, sad-sack nerds sitting in a basement that wanted to sound cool and tough, like they've just done a tour in NAM. I thought it was pretty cool. But actually, there are also other people who said that we do important stuff. So much for the promotion. Let's start with the introduction. So the requirements to do a Flip Feng Shui attack, there are basically two of them. One is we need a hardware bit flip in your DRAM that we can reproduce. For this, we're going to use Rhymer, but if at some point somebody invents another way to do this, you can also use that. And the second thing we need is the ability to target a bit flip. So be able to get something, some useful data stored in a location in DRAM that you can flip bits in. So let's look into Rhymer. What is Rhymer? How does it work? So Rhymer is a DRAM issue. It's in your hardware issue in your DRAM. And if you look at how DRAM works, then you're basically looking at cells, memory cells, or so-called capacitors. And I'm not really a hardware person, so I hope I'm not saying wrong things now. But memory cells have a natural discharge rate. So you can store, if you want to store a value in such capacitor, you're basically storing a high voltage in one of these capacitors. And over time, this voltage is decreasing until a certain threshold, where if you then want to read the voltage again, your data disappeared. So this is why we need to refresh your DRAM cells every 64 milliseconds to make sure that your data never still remains there. Now, people found that for some reason, if you have a memory cell, and if you're accessing memory cells that are very close to that one, very frequently, then the neighboring cell is discharging faster than it should be. And you can use this to do Rhymer, to trigger the Rhymer vulnerability. So let's say we have a cell that's charged, and it represents a one bit. Now you're accessing neighboring cells very frequently, and then at some point, the victim cell that has this one stored, this high voltage stored, its charge is leaking below a certain threshold, until at some point, when you read it, the victim cell, you're no longer reading a 1, but you're reading a 0. So you end up with a disturbance error. I have a animation of how this works. So this is the simplest form of Rhymer, single-sided Rhymer. This is your memory, you have cells laid out in a matrix, and if you're going to access something from your DRAM, you're accessing one row at a time. So let's say you access something, and then you're going to read from somewhere else, so nothing, and then you read again. And you repeat this a couple of times, and then you see at some point that one of the neighboring cells of this row, its charge is leaking further and further, until at some point, the one that was stored there turns into a 0. Now, some terminology. This is the row that we're reading from is called an aggressor row, and then the row that we flip bits in is a victim row. For Rhymer, it's important to note that not every bit may flip. So in this scenario, we flip this 1, 0 here, but it could very well be that this 1 here can never be flipped by doing Rhymer. It could also be that your DRAM chip is not vulnerable at all to Rhymer. But in general, once you have a bit flip, you can reproduce it. So that means that once you know that a certain cell in your memory is vulnerable to Rhymer, you can store something in there as an attacker, from an attacker's perspective, and then flip that bit to do something useful. So that was single-sided Rhymer. There's also double-sided Rhymer, and in this scenario, you're reading from 2 rows again, but now these 2 rows are sandwiching your victim row, and it turned out that this will give you more bit flips and easier or faster. But as I will explain in a minute, it's a bit harder to do double-sided Rhymer because you need to do, you have a couple more requirements. Okay, so what are the challenges for an attacker? So let's say you want to do a Rhymer attack. What do you have to do? So there are 2 things. One is you need to bypass the CPU cache. I have a slide next, but these days most memory accesses are not actually accessing your DRAM memory, but a lot of the data is stored in the cache, CPU cache. And since we're going to read from the same memory region over and over again, this data will end up in the cache. And we want to avoid that because the bug is in the DRAM. The second challenge is selecting the aggressor rows. So if we want to do this double-sided row hammer, how do we know from which memory to read from? So let's look at the first challenge, bypassing the CPU cache. So I told you the DRAM access is so slow, and the CPU caches data for fast access. But if we want to do row hammer, we must read many times from DRAM. So one solution that has been used on Intel platforms a lot is simply use an explicit cache flush instruction. So in x86 it's called CL flush, and if you execute this instruction, you basically tell the CPU, please remove this data from the cache, so that next time when I read it, the read will go to DRAM. A second option is to use a cache eviction set. And there, basically, after you've read one row into your cache, you're going to read a couple more data from DRAM. And this causes your cache to evict the first row, one of your first aggressor rows. So the next time you access that aggressor row, it will go to DRAM. It will be fetched from DRAM again. For the second challenge, selecting the aggressor rows, we need to know a little bit more about addressing, virtual addresses and physical addresses. If you're accessing data in your DRAM, you're working with physical addresses, physical memory addresses. If, on the other hand, you have a program running, and you have a buffer allocated there, then you're working with virtual addresses. And this mapping from virtual addresses to physical addresses is unpredictable. So you don't really know from which addresses in your software should I read to make sure I'm selecting the two aggressor rows to trigger the row hammer bug. So how do we figure that out? How do we know that we need to read from these two addresses? One solution is just don't and do single-sided row hammer. And then you can just pick any address and you end up with less interference between rows, so you will see less bit flips. But it was shown that this is still, in many cases, good enough to do reliable exploitation. Another solution is page map. So on Linux, you have a special file for every process that is running. And basically, this file, if you read from it, you can find this exact mapping. So you can look up this virtual address I have here in my program. What is the physical address that belongs to it? And then you can use that to find out where to read from. Another solution is huge pages. And these are virtual allocations that are mapped to physically contiguous chunks. And I think on Linux it's 2 megabytes these days. So if you have a huge page allocation, you end up with a virtual address that is contiguous, so the virtual addresses are contiguous, but also they map to a contiguous region in your physical memory. And if you know this, if you know that a certain allocation is contiguous, then you can very easily select the correct aggressor rows. Okay, so the mechanics for a Flip Feng Shui attack. The 3 things. Every attack that we do has to do these 3 things. First is memory templating. And with memory templating, we mean we're going to search memory, the entire DRAM, or most of DRAM, for bit flips that we can actually exploit. Then, when we found a location in memory, we want to plant some data there, something that is sensitive. So that's the second step of the attack, landing data at a vulnerable location. And then we're going to reproduce the bit flip and hopefully do something interesting. Okay, good. So now let's look at Flip Feng Shui, presented at Usenix by my colleagues. In Flip Feng Shui, also titled Hammering a Needle in a Software Stack, we have a malicious VM somewhere in the cloud running on a physical machine, And then this malicious VM is going to attack other VMs that are hosted on the same physical machine. We will use Rhymer to flip bits, and we're going to use memory deduplication to get a interesting piece of data at a vulnerable location. But let's assume you can flip a bit in another VM. I want you to think a little bit about what would you flip if you are an attacker, and you want to get access to another VM on the same machine. So think about this a little bit. First step of the attack, memory templating. This is relatively easy for the attacker. So you have the victim and the attacker sharing the same hardware. The attacker, of course, has root, so he can do a lot of interesting things already. He will use, so this was an x86, he will use cache flush, the explicit cache flush instruction to make sure he can actually do Rhymer. And then he will be able to allocate huge pages, so get physically contiguous memory to select the aggressor rows to do double-sided Rhymer. So the attacker does that, he allocates a lot of memory, and then starts reading from the zeros here until at some point he finds that, hey, here is a bit flip. Then the second step of the attack, land sensitive data. So now that we have this bit flip, how do we force the victim to store some sensitive data there? And for this, we are going to use memory deduplication. So I'm going to explain you what memory deduplication is. Let's say you have a victim running a program with some memory allocated, stored here, and then the attacker is running a different program also with some memory allocations here and here. When deduplication is enabled on your system, then the operating system, every now and then, will search the entire memory space for pages, memory, that is duplicate. So in this simple example, it will see that the victim here is storing this 1, 0, 1, 0, 0 in a memory location, and then the attacker somewhere else in memory also has that exact same data stored. Now, cloud providers, they really like to save their resources, right? So you want to, if you can save memory, then you can run more VMs on the same physical machine. So what did they do? The operating system, if this is enabled, it will free one of the duplicated pages, and then it will simply update the mapping from, in this case, the victim, so that it points to this physical location. And as long as this location is read-only, this simply works. And then as soon as one of the VMs starts writing to it, a copy will be made again. But this is a very useful technique, and it really saves memory. But it also, if you can do Rhymer, it will also allow you to do cool attacks. So let's say we now have a way to control data in the victim VM. Now, the question is, what are we going to store in this location? What is interesting enough for an attacker to flip one bit in? What's the two lands? We're going to land cryptographic keys. So we have thought about other things as well, for example, pointers or return addresses. But we're going to look at cryptographic keys, and we're also going to look at domain names. And this is very interesting because of this. So we're going to look at a public RSA key from the victim stored in the authorized keys file. And we're going to place that here at the location where we can flip a bit. Now, what happens if you flip a bit in a public key of an RSA key, public-private key pair? Then you change the public key. And there are crypto people here who know more about this, but basically for RSA, it works, or RSA works because you're working with two very big prime numbers, P and Q, and you multiply these, And then one of the properties of this is that it's very hard, given this one big multiplied number, to go back to P and Q. However, if you have this one big multiplied number and you flip a bit there, then all of a sudden it turns out that in many cases it is very easy to go back to P and Q and a couple more numbers. So the attacker, after he flips a bit in the cryptographic key, in the public key, he can compute the new private key that belongs to this public key, and then he can use this new private key to log in via SSH to the machine. Now, of course, in this scenario, if you're the attacker, you need to know the SSH key of the victim. There are very useful interfaces on GitHub that you can just query for public keys, so you can use that. But of course, it's still a known, it's still a knowledge attack, so you need to have some knowledge. So we have another attack where we also not only flip bits in cryptographic keys, but also in domain names. So let's look at what happens here. What happens if the victim does a apt-get upgrade on a Ubuntu machine? What happens is that it will query this website, secuirty.ubuntu.com, for example, and ask for, hey, server, do you have updates that I should install? But if this domain is stored in a location in memory where we flip a bit, then we can change ubuntu.com into ubuntu.com. And if the attacker bought this domain, which we did, he can now host malicious packages. In this scenario, we're going to host an updated core utils package. Fortunately, packages are signed, so it's not as easy as this. But we simply just also need to flip a bit in the GPG keychain to make the packages self-signed. Then the attacker can compute this new GPG key and then sign the backdoor LS. And from there on, you just have to wait as an attacker for the victim to run an upgrade. So we disclosed this in June, so last summer, with the Dutch Cybersecurity Center. They did a really good job on contacting all the vendors. So many cloud parties actually disabled memory deduplication because of this. There was also a GPG patch, so that self-signed keys are no longer valid. And in the process, we also bought all these domains that are one bit flip away from Ubuntu and Debian. I'm not sure what the current status is, but I think we're still looking for the appropriate party. Maybe Google wants to buy these domains. Because it's getting a bit expensive to have all these domains that are one bit flip away. But if you think you are the correct party, or if you know somebody who should have these domains, contact me. So then, Drammer, the second topic for this afternoon. This was presented at CCS. So this is my work. I did it when I was in Santa Barbara. I worked there with Yannick, Martina, and Giovanni. But also people here from Austria were involved, so the Grass guys, and also VU. And for Drammer, this happened when I was watching my colleagues working on the Flip Feng Shui attack, and I thought, hey, this is cool, we should try this on Android. So the question was, can we do Rawhammer attacks on Android? And if you're looking at Android, you're very quickly also looking at ARM instead of x86. We looked into this, did some preliminary study, and then we found that although Android does support memory deduplication, it is mostly disabled. So for Drammer, we're going to exploit the behavior of the underlying memory allocator, and I'm going to explain you a little bit about this. But first, memory templating, so the first phase of a Flip Feng Shui attack. What are the challenges again for x86? We need to bypass a CPU cache, so we can use cache eviction or the explicit cache flush instruction. And if we want to do double-sided Rawhammer, we can use the page map or use pages. I found relatively soon that if you want to flip bits on ARM, you actually need to do double-sided Rawhammer, because with single-sided Rawhammer, the chances of flipping bits is just too low. So we have some options here, right, on x86. Would be great if we could use any of these on ARM. So we looked into it, and does it work? Well, of course not. And because the cache eviction, for example, was too slow. So I implemented this on ARM and didn't work out well enough. The cache flush instruction on 32-bit ARM, at least, it's privileged, so you cannot flush memory from the cache from user space. The page map is privileged because Google is not stupid. They fixed this a long time ago. And then huge pages, I think they're working on it, but back then it was still not available, so it might come soon. So we had to come up with something else. And basically the solution was DMA, direct memory access. Because sometimes the CPU cache is something you don't really want. Because what happens, for example, if you have another, besides the CPU, if you have another device here, let's say a GPU or audio device or anything, that is operating on the same DRAM, the same data as CPU, then if these two devices are operating at the data at the same time, then you don't want this data stored in the CPU cache, because the CPU could be working on older data than the GPU is seeing. So this is why every operating system should have some support for DMA, direct memory access. And with DMA, you basically get uncached memory for free, so you don't even have to do any kind of explicit cache flush. For the second challenge, selecting the aggressor rows, we found that Google's or Android's DMA, the implementation, already gives us a lot of useful pinpoints here. So dedicated hardware devices might be very stupid, and if you have such simple device, then it cannot always translate virtual to physical addresses correctly. So if you want to have DMA memory sharing with one of these stupid devices, then there must be a way to have memory that is contiguous as well. So in Android, it used to be the case that you could get DMA memory that is also physically contiguous. And then it behaves very much like huge pages. So you get some allocations in your software, and this is all pointing to memory that is all contiguous in physical memory. So we could use this to address the second challenge. But then the second step of the attack, landing sensitive data. What are we going to do here? So let's look at the threat model. We're going to assume a recent Android operating system, and without memory deduplication enabled, because it's too costly to have this on a mobile device. And then we have this unprivileged app who wants to get root access. To get root access, ultimately your goal is to get read-write access to anywhere in memory. Because if you have that as an unprivileged application, then you can search kernel memory for imported data structures, and one of them being your own credential structure, and then you can override your UID with 0 to get root access. So what are we going to do? We're going to land a page table at a vulnerable location that is vulnerable to Drammer, and then we're going to flip a bit in a page table entry. So the principles of Drammer attack. I'm not going to give you the full details, but just an intuition. Page tables. Page tables are used to map virtual addresses to physical addresses. So back to the example, similar example from before, we have a simple user space program here with a simple buffer allocation, and then here in physical memory, for some reason, this word ended up above the first word, and we end up with this mapping. Now, this mapping from virtual addresses to physical addresses is stored in a page table. And a page table is really nothing else than just 2 columns, virtual address, B6A57000, is pointing to physical address 14000. The question, however, is these page tables, where are they stored? So, of course, they are stored in memory. Let's say they are stored here, somewhere in between the buffer. Now, we can read from hello and world over and over again and flip bits in this page table, maybe, if Drammer turns out to be working. But what happens if we do so? So what happens if we flip a bit in this page table? So for example, what happens if you flip a bit? What happens if you flip a bit? We can modify mappings, and for example, let's flip this 1 here into a 0. What happens is that the physical address is no longer 14000, but 10000. So the mapping that was pointing to hello is no longer pointing to hello, but is now pointing to a page table, to our own page table. And if we have access now to this page table, we can change it. And with this, we can get read-write access to anywhere in memory, because we can modify existing entries and then make this this virtual address point to somewhere else in memory where we never had access to before. Or we can add new entries to it and use this to get access to anywhere in memory. So if you have this, if you have access to the page table, then from there on, getting root access is relatively easy. The question, however, is how do you get this page table stored at this exact location? Because why wouldn't it be stored here or here? How do you get it there? And for this, in the paper we describe Feng Shui, which is a physical memory massaging primitive. And I will show you the intuition. Let's say that these are memory cells and you are running your Android phone and you have some allocations going on, so these are existing allocations. If you allocate memory on Android, then the Linux underlying body allocator will try to satisfy every allocation with the smallest amount of memory that is available. But let's look first at the first step in the attack, allocating large chunks to do actually templating. So first look at memory that is vulnerable to Drammer. So we're going to read from rows, and then at some point we find a bit flip. Now, in the following step of Drammer, we're going to allocate smaller chunks until all these small chunks are exhausted. Next, we release a part of the memory that is vulnerable, and this is also the same size as these small chunks, so that in the following step, when we actually trigger the allocation of a page table, we force the system to store it here, because this really is the only place in memory that is available for the system to store its page table. So that's in broad strokes the intuition. How does it look like when we reproduce a bit flip? People have been asking me, so I figured it would be nice to show you an example. I was lazy enough to not write for loops and checks for this, so I've been working a lot on just trying to find where the bit flip is, and it's there. And then we did some analysis on this. So we looked at 27 devices for the original paper, and we found bit flips on 18 of them. So not every device was vulnerable. And interesting enough, if you look at one device, so the Nexus 5, for example, it could be that you have a Nexus 5 with 0 bit flips, not vulnerable at all. But then the second Nexus 5 you take has close to 1 million bit flips. It could be that the first bit flip that you can actually exploit, because not every bit flip is exploitable, it could be that the first bit flip that you find that you can exploit could be after 1 second, or sometimes it is after 15 minutes. So there's a lot of variation going on there. we did some computations and we found that once you have this first bit flip that you can exploit, you can do the entire end-to-end exploit in 22 seconds. And then we wrote a Drammer test application, which we tried to publish in Google Play, but it didn't really work out. Anyway, people still found it, and people ran it. We found bit flips on the Google Pixel, so even very up-to-date hardware is still vulnerable to this Roimer. People found bit flips on the OnePlus 3, and also people were crazy enough to run this on the Galaxy Note 7 and reported bit flips there. So we contacted Google about this issue after we wrote the paper, and we did this on July 25. So why is this important, this date? It's important because it was 91 days before CCS. And Google's own Project Zero team, so the guys at Google working for vulnerabilities, they give Google 90 days to fix their issues. So we were 91 days before public disclosure, so pretty well in time. And then at some point we had a video call with them, and pretty soon in the video call they said, yeah, can you maybe publish at another venue later this year? So we said no, and then what if we support you financially, so give you some money to delay publication? Again we said no. And then they asked, okay, well, so what if you, can you maybe change some part of the paper to make it a bit more harder for other people to reproduce your tech? So obfuscate the paper. And again, we said no. But ultimately, we were rewarded $4,000. And in November, there was a partial fix. And they were going to work on a better solution. I think they already released this. However, I do think that even on the Google Pixel, you could still pull a similar attack. So in conclusion, now what? With Drammer, we've shown that we have we do widespread Roimer exploitation. That's actually a thing. You can do Roimer to break your cloud, the browser, and the mobile. And bit flips have been reported on all kinds of DRAM modules, even the ones that you can get now. Drammer gives you reliable exploitation without relying on custom memory management features like deduplication. So it's really hard to stop these kind of attacks. I want to emphasize here that we also work on defenses. So last year we broke everything. Hopefully this year we can solve everything again. The problem is that with defenses, they are not very interesting for the media to pick up. So it's important to say that we also work on stopping these kind of attacks. I think for Roimer, it's showing that software was really never designed to deal with bit flips. And the proposed defenses so far, they're still very early stages and easily bypassed. And also at the hardware level, there are some mitigations proposed, but they're still optional. And basically, I think you cannot really fix Roimer. So if you have a software bug, you can update the software, have a patch out, and then your software is fine again. But with Roimer, you cannot open your phone and then disassemble the DRAM chip, fix the DRAM chip, put it back in, and then you have a working phone again. So it's a very hard problem to fix. And I think more research is necessary on this topic. So with that, I conclude. We have a webpage at FUSEC with a lot of more information. There's an open source version of the code that gives you, that allows you to search for bit flips. Also here at the webpage, you can find the actual application that you can run on your phone and try to search for flips, see whether you are vulnerable. And that's it. Thank you.
Thank you very much, Victor. I guess we have some questions. One on the back. Here.
Hello. My question is about scalability. So we have been working a lot on Warhammer as well, and we had this question about the scalability. I would like to get your opinion about it. So basically, when you are able to have a successful Warhammer effect on one mobile, let's say on one Google Pixel, what do you think about the scalability of how much you can apply the same to same device?
So, not sure if I understand correctly. You want to know how many devices are actually vulnerable?
No. Let's imagine that you have a successful scenario on one device, one Google Pixel, okay?
Uh-huh.
And you have another Google Pixel. How much we can apply the same attack, exactly the same script from what that was working on mine on yours?
Ah, so whether the bit tips you see on one device, are they the same bit tips you see on another device?
Yeah.
Okay. We looked into this. I have data that I should be able to compare, but I didn't do that yet. So we don't really know. I think it's going to be quite random. And maybe at the, because already you have devices, if you have two the same devices, could be that one has no bit tips at all. I think if you're going to look at memory batches, so actual physical DRAM chips, then that might be more, then you might be able to see something there.
Okay, thank you.
All right. Hi. Two questions for Revolut again. First one is, how easy it is to find an area in which you can really do a bit flip? I mean, it seems that you have to know a little bit of structural information that's stored there, because otherwise you would just say.
So just finding the first exploitable bit flip, you mean, or just a bit flip at all?
Yeah, finding one. I mean, you're injecting information that are related to data structure that are already stored in your memory. So if you don't know the data structure, how can you really figure out where to inject?
So for finding the bit flips, you don't need to have, you don't need to do anything for this. You just asked Android to give you some DMA memory, and then you just write values to it, and then you basically read from it, and then you observe whether somewhere else in that same chunk you see bit flip. And then for the, as soon as you want to land this page table structure, yeah, that basically with the Feng Shui approach, it's very easy to get it at the exact correct location in memory.
Okay. Second question is, you said that when the first one was found, then the other ones were coming after 20 seconds, more or less.
Ah, no. The so not every bit flip is exploitable, because in the page table you need to have the bit flip at the exact location to make sure you actually can let it point back to something you control. But once you have that, once you have a bit flip that you can exploit, which you can all compute beforehand, then from there on, so you get access to a page table, and then you need to scan the kernel memory for important data structures. And there's some ASLR there, so you need to do some brute force searches, and that takes at most 22 seconds.
Okay, thanks.
Thank you for the talk. One question, you mentioned that you explored the hardware protection, and still, even with hardware protection, the raw hammer attack is possible. So I'm interested in this ECC memory, if with ECC memory, this attack is still possible.
That's a very good question. In general, no. But also I would like to say that we, also with the other hardware defenses, if they are deployed, then they should be able to stop Drammer attacks. So the problem is that, so ECC, you won't see it soon, I guess, in phones, but the other mitigation that's there, it's still optional. And even if the DRAM might be shipped with this mitigation, then the chip manufacturer may decide not to use it at all. So that is why, even if you have these defenses in place, they're working on it, they're still not really deployed.
So with ECC enabled, it's not possible?
I wouldn't say it's impossible, but it's going to be a bit harder. I'm not sure if I should make a claim that it's not possible. No. If you have, for example, more than one bit flip in the same region that's used for the ECC checks, then you might be able to bypass the ECC check.
Thank you.
So we have one last question. Okay, then thank you very much again. Thank you.